Welcome back. In the last class we developed expressions of multiplicity for simple system. In this lecture we are going to learn how this multiplicity and particularly maximizing the multiplicity with or without the constraints are related to physical processes. Okay. So, let me just first summarize what we have done in terms of the development of expression of multiplicity. We use simple systems such as head and tail systems, and we developed a multiplicity particularly for let us say a composition of coin flips, which can be given by this expression. Okay, where n could be number of head and capital N would be the number of outcomes. Okay, that includes heads and tail. So, this is a simple expression of multiplicity. Okay. Now, if you increase n, okay, let us say from a small number to large number, and let us say you plot w as a function of small n, okay, which again, as I said, could be number of heads or number of tails out of capital N outcomes. So, you could see that this expression can be obtained, which will look like this if you connect the histogram maximum points, and as you increase the capital N, what you are going to see is basically that distribution will be around the n by 2 value, okay, as shown here, and it will be peaked around it, which is going to be sharp peak. Okay, as clearly from this geometric representation, you can clearly see the maximum occurs at n star is equal to n by 2. Okay, n star is equal to capital N by 2. So, the multiplicity distribution becomes increasingly peaked as you increase n. And now, why this is important? Because we would soon learn that maximization of w or the multiplicity or logarithmic value of the w serves the same predictive role as the minimization of the energy in order to obtain the optimum value of a variable for a given system. So, with this we can ask a couple of questions and understand the importance of this concept. For example, why do gases exert pressure? Now, imagine a gas of n spherical particles that are free to distribute throughout the either large volume or a small volume. The question would be, why does the gas spread out in the larger volume? That is something which we have intuition about it. Okay, but how do you explain that using the multiplicity concept? So, we are going to consider 3 systems here. So, let us consider 3 cases A, B, C for a given number of gas particle which occupies different volume. Okay, and here the gas can occupy lattice side in one dimension. So, what we have done is the volume itself is divided into different latticed sides. So, this becomes one lattice side, this is another lattice side, and this is another lattice side, and the particle, which in this case are only 3 gas particles, can occupy only one lattice side. So, let us assume that you have total number of lattice side is m, okay, and now you have 3 which can vary depending on the volume which you have, and here you have 3 cases A, B, C. Okay. So, the volume in the A is going to be 5 because they have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 lattice points. Here they are 1, 2, 3, 4 lattice points, and here you have 3 lattice points. Okay. Now, considering these, one can say that while the number of possible ways to arrange on the multiplicity in this case will vary, okay, and will vary the similar form as we have shown earlier. Okay. So, in this case, what is WA? WA would be 3 out of 5 lattice point, WB would be 3 out of 4, and WC would be 3 out of 3. So, in this case, there is only one possibility, okay, because it is indistinguished. All the particles are of same type, and hence it is indistinguishable. Now, the maximum possibility is basically 10, and hence it tries to expand in order to maximize the number of ways it can arrange itself, and this is clearly seen by the number of W, where this is maximum for the case of A, indicates that the gas like to spread out, or the gas particles like to spread out in order to access more sites, which would lead to the increase in the multiplicity. Okay. So, that is the case why the gas spreads out into a larger volume. So, that is the case or example 1. Another examples, and try to explain the phenomena based on the maximizing multiplicity concepts. For example, why do material diffuse? Suppose that you have 4 black particles and 4 white particles in 8 lattice sites. So, there are 4 lattice sites to the left and 4 lattice sites to the right, and this left hand side regions are separated by a permeable wall. Okay. So, let us say this is the left region, this is the right region, okay, and this in between there is a permeable wall. Okay. And as I said, there are 4 black particles and 4 white particles. The volume is fixed and all the lattice sites are filled. How would the particle organize? So, what would be the condition for, let us say, an equilibrium? So, we consider, let us say, in order to understand this why particle diffuse, or what is the best scenario for an equilibrium condition, we consider just 3 cases. In the case A, you have 2 black on the left and of course 2 black on the right. In the case B, you have 3 blacks on the left. In the case C, you have all the blacks on the left. And then we ask this question that what is the multiplicity of WA, B and WC. So, this would give an indication that which scenario would be more preferred. So, we simply calculate the multiplicity in this case by finding out the multiplicity of the left region multiplied by the right region. Okay. Because these are kind of independent here. So, the number of ways you can arrange in the left multiplied by the number of ways you can arrange in the right would be the total number of multiplicity for the given condition, for the given case here. So, we can simply use the same formulation as we have done earlier. So, this would be your W in this case is 2 4 multiplied by W again 2 4. Okay. Whereas, in this case there are 3 blacks out of 4 regions. So, there should be W 3 4 and this is again would be W 3 4 or 1 4 or 1 4, this would be same. And similarly, this will be your W 0 4 or 4 4, and you can clearly see in this case the WA has the maximum multiplicity, which indicates that the mixing of this particle from initially you had the black in the left region, white in the right region. So, white particle or black particle such that it allows a mixing of this particle, increases the multiplicity, and this is the reason that the materials diffuses in order to maximize is multiplicity. Okay. So, this means this is more probable scenario, okay, at equilibrium. Now, we can also ask a very interesting question, that why the rubber is elastic, and you know that when you stretch a rubber band, it pulls back. Okay, it does not remain at the initial maximum stretching length, it comes back, but it does not go back to the original length, it stays in the intermediate length. The retractive force is due to the tendency of the polymer to adopt conformation that maximizes their multiplicity. That is our assertion, and we are going to show that intermediate configuration maximizes the multiplicity. Okay. And because polymer can have a fewer conformations when fully stretched, in order to show that, we can consider a simple model. Okay. So, this model is very simple. So, you have a 3-bit particle, okay, which is attached to a wall, because this wall could be your hand in which you are using it in order to stretch. Okay. And now, this L is the length away from this wall. Okay. So, when this is 1, it means you have a scenario where the one bond is attached to this and this is related to this. Okay. So there is only two possibility, either you can arrange it in this way or in this way, either in this way or in that way. The intermediately, when you consider, let us say 2, L is equal to 2, that means you have scenarios such that the length from here, so 1 and this is another one. So you can have scenario, okay, something like this, where you can consider in this way, okay, that means it has to bend from L equal to 2. Okay, so this is one length, this is another length, and it will bend here or in this side. That is what it is done here. Okay, this is one possibility. The other possibility could be that you have extension here and then it is bent in this way. This will also give us length is equal to 2. Okay, that means this is an intermediate configuration. This is what exactly is being done. So there are two ways you can arrange in this form. Okay, and you can arrange this and this in this two form, where there is a bending in the first region, and there is alternative form is this one. So in total you can arrange this in 4 ways. Okay, so one in this way, so this could be 1, the other side would be 2, and here this could be 3, and if you do the same way it could be 4. Okay. Now when you have L equal to 3, since it is a 3-bid polymer chain, this we call it bead, so there is only one conformation. So this is going to be L equal to 3. There is only one possibility. With this the multiplicity having conformation with L equal to 1, that means close to the wall, there are 2. With L equal to 2 there is 4, with L equal to 3 there is 1, indicates that this is the most preferred conformation where the multiplicity is going to be maximum. Okay, and this is primarily the reason why when you stretch it come back at the intermediate length. Okay, so with this basic understanding, let me just formally define entropy in terms of multiplicity. Ludwig Boltzmann introduced the following expression, where entropy is proportional to the logarithmic value of the multiplicity, where the constant of proportionality is k, which is called Boltzmann constant. Okay, k, and its value is given as here. Okay, now it is very interesting, rather it is a remarkable expression, because here you have this as a macroscopic thermodynamic property, and W is a macroscopic degree of freedom of the system or multiplicity. So this is a relation which connects macroscopic thermodynamic property to a microscopic property, and sometimes also called bridge equation. So now let me connect this entropy to the probability through the expressions of multiplicity. So let me consider a case of rolling of a t-sided die n times. Okay, so using the concept of multiplicity, we can write this W as n factorial divided by the overcounting values of this t-sided, that will be your n1 factorial till n t factorial. Now in order to solve this, we can use this Stirling approximation, which is valid for very large values of n, and here we can write n factorial as n by e to the power n. Okay, that is what is written here. Now you can take out the denominator e to the power n, and also you can take out from here e to the power n1 till e to the power t. Okay, and since n is equal to sum of this n1 to nt, that e in the denominator will cancel out. What remain would be just simply n1 to the power n1, n to the power n2, and so forth. Okay. Now we can now write down this expression in terms of probability. So if we define pi, probability of a state I or side I, as simply ni divided by n, okay, in that case you can divide this by n, and this will get cancelled out in the way that it can be written as simply n1 by n to the power n1 till nt by n to the power nt. Okay, which means I can write this expression in this form. Okay, Now this further can be simplified by taking a logarithmic value of W, and now using this Boltzmann expression, okay, if I divide this by n, I can write this as, because this, if I write it here, this will be simply summation Ni ln Pi, okay, for I equals to 1 to t. If I divide by n, I am going to get n here, and this is going to be simply Pi ln Pi, I is equal to 1 to t with a negative sign. Okay, this is what exactly is written here. Now this expression, okay, can be used to, in order to get entropy by n, which now can be written as here per particle, and this is nothing but this expression. Okay, so we have got an expression of entropy for such a system where it can be connected to the probability of the outcomes of different events here. Okay, so in the absence of constraints, equilibrium states corresponds to those states with the maximum entropy. So given this, what does this scenario imply for the distribution of probability? In other words, what would be the Pi when in a limiting case? Okay. So now, in order to understand this, we will consider flipping of coin. So what does pH approaches for a large value of n, that is the limiting case? That is what we are asking the question given this information, and we know that for the case of no constraints, the maximum entropy would be the case, and this is something which we can show that Pi approaches toward of course 1 by 2, that we can show that, but I will come back to this in the later stage. But we can try to do an example using this expression in order to find more likely conditions of a state. For example, if you consider spinning a pencil n times such that on a table such that it can align in 4 quadrants, and if you define these 4 quadrants as north, east, south and west, then let us consider this 4 different scenario. One would be the order that every time you do that you obtain n, in that case your Pi is 1. Okay, so this you have done this many times, so you have 4 different possibilities in this case which we have considered. So this will be the ordered case. If it lands only in east and south with the probability half and half, this will be your bias case, and if it is in such a way that it prefers more north and west, it will be again a bias case, and this is a case where it is a random, that every quadrant has every quadrant gets equal chance or will have the same probability. Now in order to find out the most likely distribution of state in such a case, we can calculate entropy. So entropy per particle is simply minus k summation Pi ln Pi, or S by k is summation Pi ln Pi with a negative sign. So if you use this information, you can clearly see S by k is equal to 0. In this case S by k is 0.69, in this case S by k is 1.33, and in this case S by k is 1.39, and this is the one which has the maximum value of this entropy, and thus indicates that this is going to be the likely distribution of state without any constraint put on the system. Okay. Now we can generalize this by considering cases where you may have constraints, and in such case how do you optimize this function w, or in general any function, let us say f, okay, which is a multivariate function which may depends on different variables such as x1 till xt. Okay. So if you consider such a function with t variables, and let us say you have 2 constraint g and h such that g is equal to c1, g also depends on these variables, these t variables, and h also depends on t variables. So in order to find this optimized value of the function for these 2 constraints, given constraints, we will be using the method of Lagrange multipliers. In such case what we do is basically either we think of so in such case what we do is basically we take the derivative, first derivative of this function f with respect to different variables in this form. So, this is this kind of a set of equation to be solved. So, this is for example del f by del x minus lambda del g by del x1 minus beta del h by del x1, and lambda and beta are unknown variables which we need to find out. And similarly, we have to take this first derivatives with respect to different variables up till xt, and this must be equal to 0 in order to get a maximum value of such a function given constraints g is equal to c1 and h is equal to x1. We can simplify this expression by writing in this form, that one can use, instead of doing this, one can use this condition that the total differential of the function is to be optimized and the constraint function must be 0 to develop the following expression. That means f minus lambda g minus beta, this differential should be 0, okay, in order to have or at a maximum value of the variable leading to this function to be 0, and this you can write this expression in terms of the summation of 1 to t. T is the number of variables, the first derivative with respect to xi minus lambda and minus beta, okay, and del x c1. This is nothing but the same expression as you have got it. If you rearrange this, you should be able to get this expression again. Okay, so this is nothing but the method of Lagrange multiplier without deriving how this has been approached or obtained. We are just going to use this in order to find out the maximum value of the function or optimize the function for a given constraint. Now, let us look at how to make use of this method in order to find out the maximum value of the probability for different conditions, that means with constraint and without the constraints. Okay. So, let us examine the probability distribution that arises by maximizing the entropy when there are no constraints. So, when we do not have any constraints, so that means external constraint, we still have one particular condition which must be satisfied, that is summation of pi should be equal to 1. In other words, dpi should be equal to 0. Okay. So, we now have to optimize the function using Lagrange multiplier method. Now, we know that S is equal to summation pi ln pi. Remember that we have considered in this case S by k, and we have taken k is equal to 1 for the sake of simplicity. Okay. So, this as depends on from py till pt. Okay. Now, using the Lagrange multiplier method, we need to remember that what we have done earlier. So, this is your function s here, and this is your function the summation pi is equal to 1. So, if you take a differential of this is going to be simply dpi is equal to 0. That is what it is. So, if you do this exercise, use instead of f, and f is nothing but your s here. Okay. So, we put here f here. Okay. So, this is the first derivative del. Remember again, let me just reproduce here lambda, because there is only one variable, and this is going to be del g by del xi. Okay, look at it here, right, and this is going to be dxi. This must be 0. So, if you look at the expression, this is going to be del s by del pi for all of the pj not equal to y minus l lambda, and this is going to be simply del g by del pi, which is going to be only 1. So, this will be 1 multiplied by dpi. Okay. Now, from here we need to solve this problem, this expression. Now, this expression can be evaluated from the fact that your s is equal to s by k, k is equal to 1 is minus pi ln pi. So, if you take the derivative of this, you will get del s by del pi is going to be only this expression, because you are going to differentiate with respect to pi only, the rest is going to be 0. So, this is going to be pi 1 minus pi, okay, with a negative sign here, and then this is going to be ln pi. Okay. So, now from we have to get this expression, okay, and this expression we can calculate from this the definition of the entropy with as a function of the probability. From here, if you take the derivative of S with respect to Pi, then you can show that this is nothing but only this one term will remain here and the rest will be 0. And if you take the differentiation of this part, this would be Pi multiplied by 1 by Pi plus ln Pi. Okay, and this is going to be 1 plus ln Pi. So if you plug in here, you get this expression. Now you, in order to solve this, you have to plug in this part, but remember that this 0 indicates that this will be 0 as well, because the rest of the i's are a different event. So if this is 0, which means basically this, or rather this minus alpha should be 0, and this is a condition which gives us that if you rearrange this itself, is going to be ln Pi is equal to minus 1 minus alpha, or Pi is equal to e to the power minus 1 minus alpha. Okay, and this is going to be the optimal value of Pi, because we have just got an expression which is maximum. Okay, and for the probability this, and that's why we are saying this is the optimum value of Pi. Okay. Now major problem is that we don't know what is alpha. Okay, so in order to get the alpha, what we can do is we can go back to the normalization criteria that sum of the Pi should be 1, sum of the Pi should be 1. So we plug in this expression Pi. So we know that is sum of this Pi should be 1. So now if we consider this it to be e to the power minus 1 minus lambda, so I can write this as Pi, because this is equivalent of saying this is lambda divided by 1, and now I can get rid of alpha. This is going to be summation e to the power minus 1 minus alpha, alpha being constant here, I can take it out, e to the power minus alpha e to the power minus 1. Okay, and this is going to be e to the power minus alpha summation e to the power minus 1. So this gets cancelled. So what we have is basically this will also get cancelled, and this is going to be only summation 1 I is equal to 1 to t, which is nothing but 1 by t. So in such case your probability distribution says that it is 1 by t, or normalized, or basically the random or equal probability for all the side. Okay. So this is something which we have seen the case when we had this pencil randomly rotated for this 4 quadrant, and we obtained 1 by 4 as an option. Similarly, if you consider two events such as head and tail, if it is non-biased, you will see that Pi star is going to be 1 by 2. For all this case, if you have t outcome and you are looking at the normalized or limiting condition where this P is going to be optimized, where the entropy is going to be maximum for such a P, and this P is going to be simply 1 by t. Okay. So we can extend this exercise. Now instead of considering without any constraint, we consider with one constraint. So let us examine the probability distribution that arise by maximizing the entropy when there is a constraint in addition to normalization condition. So so what is the constraint? So let's say we are aware of a average property of energy, okay, and we wish to estimate the probability distribution that would result in such an average. Okay, so you have to optimize the entropy, but now the delta E is given to you, and we have to find out the probability which would lead to such a condition where the delta E would be the final value of the average energy. So what is the delta E, average value of E is E by n, and that can be written as simply the weighted average of this, or the first moment, okay, of the probability distribution, which is Pi epsilon I, because assuming that Pi is normalized. Okay, so now we have to consider maximize the entropy. So this is P1, P2, and this is dot dot till Pt. This is we know, this is we have to maximize, but with the constraint that summation P is going to be 1, that is your G function, and H function is that summation Pi epsilon I is known value, which is average value of E. So now we go back to the same expression of the Lagrange multiplier here, and remember that for Lagrange multiplier for each term we have written this, right, dpi. So this internal or this part must be 0. Okay, this part must be 0. Now we have to find out the first derivative s, g and h. So what is the first derivative h, s, which will remain the same as we have obtained for the case of non-constraint, which will be simply -1 minus ln pi. What about g? This is going to be 1 because this is summation pi equal to 1. And what about the h? Okay, this will be simply epsilon I. Okay, so if you take a derivative of this expression with respect to the pi is going to be only epsilon I. So we plug in this expression and we got this expression. This is due to the first term, this is the second term, and this is the third term. Now we got an expression of pi now, which comes from here. If you take from here the last one, you're going to get e to the power minus 1 minus alpha minus beta epsilon I. Now again we make use of this normalization condition in order to remove the alphas. We consider summation pi equal to 1, that means this we divided by this expression, and here we separate this part, and for numerator the same part gets cancelled. So what remains is this, and this is nothing but pi star. Now this expression is a very well known expression. Okay, this expression is called Boltzmann distribution. Okay, and what we have seen, what we have developed here is basically that the probability of a state having an energy E is nothing but the Boltzmann factor, which is epsilon exponential of minus beta epsilon divided by the normalized or the sum of all the probabilities. Or in other words, the probability distribution is nothing but the normalized value of the Boltzmann factor. Okay, because this is the sum of the probability of all other states. So this is a beautiful expression which have come for the constraint values. Okay, now this expression is also called as partition function. Okay, this is also called the partition function. Okay, and now we can write this epsilon average E as simply pi star epsilon I, which can be written as E epsilon I multiplied by the Boltzmann factor divided by the partition function. So this is now the way to calculate epsilon for this system having a constraint. Now this is a common approach in statistical mechanics. Now we can apply to many different systems. So in the next lecture I will formally define the statistical mechanics, and we'll be using this such an expression for molecular systems. Okay, so with this I will stop today's lecture. So see you next time.